Welcome to this session on electric discharge machining, particularly wire cut electric discharge machining under the course Advanced Manufacturing Processes. In the last session, we have discussed about the basics of electric discharge machining process, its principle, features, the mechanism of material removal, advantages, limitations and few applications. In this particular session, we will study about the DieSinker and WEDM process, also known as WEDM, the process parameters, applications of this process, advantages and limitations of WEDM process. Also, we will see some hybrid EDM processes and their variants. Let us move ahead. In the very beginning, let us see the different types of EDM. Commonly, there are two types of EDM processes. One is DieSinker EDM and the other one is known as wire cut EDM, also in short known as WEDM. Let us look into the DieSinker EDM. This process is generally used for producing blind cavities. Here the electrode and the workpiece are submerged in an insulating liquid known as dielectric fluid. So, principally this is similar to that of common EDM process. The DieSinker EDM is also known by different names such as ram EDM, sinker EDM, vertical EDM and plunge EDM. The insulating liquid used in DieSinker EDM completely submerges the electrode and the workpiece. Some special oils, special dielectric fluids and deionized water can be used as the dielectric. The electrode and workpiece are connected to a suitable power supply. An electrical potential is generated between the tool and the workpiece through the power supply. As the electrode approaches the workpiece, the dielectric breaks down. Due to this, a plasma channel starts forming and the sparks jump from the electrode to the workpiece, leading to the material removal from the workpiece. The principle of die sinking EDM is shown in the following figure along with the schematic in the next. Therefore, we have seen almost the principle of working in the die sinking and the normal EDM are equivalent. The main component in die sinking EDM are power supply, dielectric system, electrode, the servo system. So, this is the schematic which explains the principle of sparking. So, this is the electrode and this is the workpiece which is usually connected to the positive terminal of the power supply, and here the shape of the tool is shown different and this same shape will be replicated on the workpiece as well, and the sparking will take place through the different zones or the distances through different points which are closer to the workpiece, and this sparking, that is the plasma formation zone, will create the bubbles and high pressure which will collapse subsequently and erode the workpiece on wherever the sparking is taking place. The erosion of the workpiece will also take place. Of course, as we have seen in the case of EDM, small erosion will take place on the electrode as well. So, this is we can say this is the tool or the electrode and this is the workpiece, and this is how the dielectric fluid moves into the cavity and the debris are coming out from the cavity as a result of the machining here and the flowing fluid here. As we remove the tool, the dielectric enters inside this, and as we enter the tool inside this, the sparking does take place and the debris are created, which are subsequently taken away by the flowing dielectric fluid. The power supply in this arrangement provides a series of DC electrical discharges, and it also controls current, power, pulse voltage and the pulse duration. As I have already told, the pulse power supply is very important in the case of EDM. So, this is pulses are like this, like this. So, this pulses, these are known as pulses, and this is the off time and this is the on time of this pulse, and during this time the erosion will take place, erosion on the workpiece as well as to some extent on the tool will take place. And during this off time, the debris will be removed, and fresh dielectric is flown into the IEZ, that is known as inter electrode gap. And by design we can change this time T on and T off. This time can be changed by design of the circuit and by adjusting different parameters in the control circuit, and this depends on the requirement of the machining process. The power supply provides a series of DC electric discharges. It controls the current, pulse voltage, the pulse duration, duty cycle, the electrode polarity and as well as the pulse frequency. The dielectric and its circulation system, also an important subsystem of this entire machining setup. Different types of dielectric fluids are used in EDM operations. The most common and popular being the hydrocarbon oils, that is kerosene. In order to provide circulation of the dielectric fluid to the workpiece, the EDM machine tool is equipped with a well designed dielectric circulation system. The dielectric circulation system consists of the following two major parts. Number one is pump. Its main purpose is to circulate the dielectric fluid onto the workpiece, and number two is filter and the suction unit. As I have already told, there should be some filtering system to remove the debris present in the dielectric fluid. This unit filters out the material debris and any other foreign particles that may come in contact or present in the dielectric fluid. Next is the servo system. The servo system is commanded by signals from gap voltage sensor system in the power supply. It controls the infeed of the electrode to precisely match the required rate of material removal. At times, stepper motor can be used instead of a servo motor. Once the gap voltage sensor system determines bridging of the some pieces of electrically conducting materials between the electrode and the workpiece, immediately the servo system reacts and reverses the direction. That means, it retracts the tool so that the short circuiting of the gap does not take place. As I have already indicated, if the short circuiting does take place, then there will not be any sparking, and therefore, we will not be getting the desired erosion effect in the working zone. The process is restored when the gap is flushed by the dielectric fluid. When the gap becomes clear, the infeed resumes and the cutting process continues. Let us look into the electrodes. The electrodes for EDM process are usually made of brass, copper, graphite and copper tungsten alloys. In EDM process, fine openings and deeper slots need to be avoided. Design considerations for EDM process. In EDM process, fine openings and deeper slots need to be avoided. Very fine surface finish values should not be specified, as we have already discussed. EDM is a coarse material removal process basically, and is not recommended for fine finishing of surfaces. As the MRR or the material removal rate of EDM process is low, the rough cutting should be done by some other machining process. This will save the machining time and add to the economy of the process. In cases where bigger holes are to be manufactured in hard materials, hollow tools can be prepared, which can save the material, and the obtained cylindrical pieces can be used for other applications. This can be explained like this. Say for example, in a workpiece, a big size hole is to be through hole is to be produced. This is the hole diameter. Now, for this, instead of using a solid tool like this, whose cross section is solid like this, so we can use a tool having hollow cross section, something like this. So, this will have the cross section like this, and therefore, this is not suggested in this case, and therefore, what will happen, the sparking will take place on this through this cross section, and a cutting will take place correspondingly on this zone, and this piece, this in between piece will come out as the waste like this. So, this will be the waste piece produced in this process. If we use this kind of cross section for machining of this hole, then the sparking will take place only through this, leaving behind this material in between as uncut material, and this will be obtained as an extra piece or the waste piece, which can be further used for some other material removal processes. This process, why this process is suggested is that in at times this process is even faster than the process used with the solid tool. This is a solid tool and this is a hollow tool. And at times this is considered to be faster and therefore recommended for some such applications like this. Now, let us move into another category of EDM, that is wear EDM. This process is mainly used for cutting applications, making slots and fine features on hard blocks. It uses a continuous pool of wear and water is used as the dielectric fluid. It is also known as wear cut EDM. The wear electric discharge machining, shortly known as WEDM, is a variation of basically the EDM process and is commonly known as wear cutting. In this process, a thin metallic wear is fed into the workpiece, which is submerged in a tank of dielectric fluid such as deionized water. This process can also cut plates as thick as 300 millimeter. Therefore, this is considered to be very useful process. It is also used in making punches, tools and dies from hard metals that are difficult to machine with other methods. The wear, which is constantly fed from a spool, is held between the upper and lower diamond guides. The guides are usually CNC controlled and move in the XY plane. On most machines, the upper guide can move independently in the Z, U and V axis, giving a flexibility to wear cut, tapered and transitioning shapes, for example, square at the bottom and circle on the top. The upper guide can control axis movement in X, Y, U, V, I, J, K and L. This helps in programming the wear cut EDM for cutting very intricate and delicate shapes. In the wear cut EDM process, water is commonly used as the dielectric fluid. Filters and deionizing units are used for controlling the resistivity and other electrical properties. Wares made of brass are generally preferred. Water helps in flushing away the debris from the cutting zone. The flushing also helps to determine the feed rates to be given for different thickness of the materials. Let us see the schematic of this process as in the screen. This is the wear we were talking about. This is nothing but a wear of material brass or something like that, and this forms actually the tool which is also connected to one end of the power supply, and this is the workpiece which will be eventually connected to the other end of the power supply. That means, this wear and this workpiece forms the pair of electrodes in this case. Now, this wear will be constantly fed through a spool arrangement. It will be continuously moving from one spool to the another, and there is a separate mechanism for this, and this keeps always a fresh portion of the wear to come in contact to the working zone. Otherwise, if it is kept at the same position, the wear will also get eroded very fast and the continuity of this wear will get vanished. It will be broken in between. Therefore, the fresh piece of the wear will come always in this cutting zone, providing a better sparking condition in the working zone. This workpiece is connected to the table, work table, which can be controlled in x, y, z directions like this as shown in this figure. Generally x and y will be controlled here, and basically any profile with the help of this movement of this x, y can be cut on this workpiece as shown here. This motions of this work table and hence the workpiece can be controlled or programmed through CNC machining device. The WEDM process requires lesser cutting forces in material removal. It is generally used when lower residual stresses in the workpiece are desired. If the energy or power per pulse is relatively low, as in the finishing operations, then very little changes in the mechanical properties of the materials are expected due to these low residual stresses. The materials which are not stress relieved earlier can get distorted in the WEDM process. The selection of process parameters is very crucial in this process. The workpiece undergoes significant thermal cycles. These thermal cycles can be considered very severe from designing point of view. The thermal cycles can form recast layers, as we have already discussed while discussing the basics of EDM process, and induce residual tensile stresses on the workpiece surface, which are at times or most of the times undesired. Now, let us see the process of material removal in wear cut EDM process. In the wear EDM process, the motion of the wear is very slow. It is fed from the programmed part and material is cut or removed from the workpiece accordingly. Electrically conductive materials are cut by WEDM process by the electrothermal mechanisms. Material removal takes place by a series of discrete discharges between the wear electrode and the workpiece in the presence of a dielectric fluid, which we have already discussed as in the case of normal EDM. The dielectric fluid gets ionized in between the tool electrode gap, thereby creating a path for each discharge, also called the plasma column. The area wherein discharges takes place get heated to very high temperature, such that the surface gets melted and removed. The cut particles or the debris get flushed away by the continuously flowing dielectric fluid. The WEDM is a non-conventional process working on the basics of EDM principle. It is very widely used in tool steels for pattern and die making industries. The process is also used for cutting intricate shapes in components used for dielectric and aerospace industries. Let us see the applications, common applications of wear cut EDM. It is used for cutting materials like aluminum, brass, copper, carbides, graphite, steels and titanium. The wear cut materials varies with the application requirements. For example, for quicker cutting action, zinc coated brass wears are used. Molybdenum wears are used for more accurate applications. The process is used in the following areas: aerospace, medical, electronics and semiconductor applications. Tool and die making industries, the wear EDM is highly preferred. For cutting hard extrusion dies, wear EDM is usually preferred. In making fixtures, gauges and cams, cutting of gears, strippers, punches and dies, and manufacturing of hard electrodes, this wear EDM is generally preferred. Other applications of this process include manufacturing of micro tooling for micro EDM, micro USM and such other micro machining applications. One such applications like cutting of laminated sheets is shown in this particular figure as in the screen. So, number of plates are being placed stacked in this configuration and the wire can be cut or moved through this stack of sheets or laminates, making a slit. Thus, if a particular pattern is to be cut on this number of laminates, then the wire cut is a very effective or useful process. Now, let us see the subsystems of wire EDM system. As in the case of EDM, power supply, dielectric system, wire feeding system and positioning systems are used in this wire EDM setup. Here the wire feeding system is an addition to what we get in the normal EDM process. The power supply and dielectric system used in WEDM is very similar to that of the conventional EDM, as I have been already telling. The main difference lies only in the type of dielectric used. In wire cut EDM, a moving wire electrode is used to cut complex outlines and fine details in the required workpiece. The wire is wound on a spool and is kept in constant tension. The drive system continuously delivers the fresh wire onto the work area. New wire is continuously exposed to the workpiece. Hence, the wear of the wire, which is a tool here, is not the major issue in this process. The wire feeding system consists of a large spool of wire and rollers which direct the wire through the machine. The presence of metal provides power to the wire and guides it further in order to keep the straight throughout the cutting process. Other parts in this setup are the pinch rollers which provide drive and wear tension, a system to thread the wear from the upper to the lower guide and a sensor to detect when the wear runs out of or breaks. Now, let us look into the process parameters in WEDM process. These process parameters are shown in this familiar figure. These process parameters are grouped into 4 main categories: electrical parameters, which are pulse on time, supply voltage, peak current and pulse off time, and dielectric based parameters like type of dielectrics, viscosity and then flow properties. Then other non-electrical parameters are like gain, flushing and lift. Electrode based parameters are the size of the electrode and the material of the electrode, conductivity of the electrode and so on. Electrical parameters include peak current, pulse on time, pulse off time, supply voltage and polarity. Non-electrical parameters include wear speed, work feed rate, machining time, gain and rate of flushing as well. Whereas electrode based parameters include material and size of the wear. The dielectric system based parameters include type of the dielectric, viscosity of the dielectric and other flow characteristics. Let us see some other applications of this WEDM process. This process is useful for cutting intricate mold cavities and difficult to machine parts. The process is widely used also for machining of exotic materials that are used in aerospace and automotive industries. EDM being a non-contact type machining process, it is very well suited for making fragile parts which cannot take the stress of machining. The part that fit such profiles include washing machine agitators, electronic components, printed parts and difficult to machine features such as honeycomb shapes. Deep cavities, slots and ribs can be easily made by EDM as the cutting forces are less and longer electrodes can be used to make such collets, jet engine blade slots, mold cooling slots, etc. Micro EDM process can successfully produce micro pins, micro nozzles and micro cavities. As we know, these are some of the applications like producing micro pins for micro machining, micro nozzles and micro cavities are otherwise very difficult to machine using other conventional techniques, but here this process where EDM can be very useful. Now, let us see few specialized applications of this EDM process. Some problems are like this. Most of the times while machining big steel or cast iron workpieces and manifolds, small drills or taps get broken inside the hole while performing larger length holes, and generally this can lead to rejection of the entire block, which is a sheer wastage of money. However, there is an alternative provided by the EDM process in such cases. As the EDM is a localized machining process, it can be readily used for removing the broken tapes and drills or tools from the passage. In order to achieve this task, a suitable tool little smaller in diameter than the embedded tool size is prepared and the block is machined by EDM on this localized area. The hard material melts, evaporates and gets flashed away due to the generated sparks. This saves the replacement cost of such large blocks and they can be repaired without much harm to the desired features. Now, let us also look at the limitations of this process, wear EDM process. Every cutting requires new stream of wear, as due to the continuous discharges the wears used in WEDM become non-usable and are not recirculated. They tend to become a waste and add up to the cost. In between stoppage due to the wear cut leads to time loss and wear wastages. Now, let us summarize what we have discussed in this particular session. In this session, we have discussed in details the common types of EDM, the DieSinker and the wear EDM processes in particular, typical applications of these processes, the process parameters that affect the machined product using these processes, and the limitations of these processes have also been discussed. We hope this session was informative and interesting. Thank you.